let's start. Okay, the recording, and it's my great pleasure to introduce Professor Sergey Denisov from the University of Wisconsin-Madison. The title of his talk is Studying Wave Operators Using Complex Analysis, Some One-Dimensional and Multidimensional Results. Please.
Okay, thank you. Thank you for introduction. It's a great pleasure to speak at the conference. And thank you, organizers, for inviting me. So, yeah, I will start with giving some references, and a lot of this work has been done with Roman Bessonov from St. Petersburg. And the talk will be divided into two parts. So the first part will be about one-dimensional setting, and the second part about PDE. Okay, so let's start. And so that's roughly the plan of my talk. So we'll start by saying what are the wave operators and what are they good for. Then we'll talk about 1D results, and we will focus on Dirac operator. And after that, I will start talking about the multidimensional results. And somehow the punchline will be that we'll have to combine techniques of partial differential equations and complex analysis, but this complex analysis is not going to be complex analysis of scalar analytic functions, rather vector valued analytic functions. And the Hardy spaces will not be scalar Hardy spaces, rather this will be vector valued Hardy spaces. So I'll talk about that later, and I'll try to explain the main ideas. Okay, so let's start. And as promised, I will start by giving you some brief overview of what are actually the wave operators. So we can start with very, very general setting. So suppose we have a Hilbert space, and we have two self-adjoint operators in this Hilbert space. So one is H naught, and we typically refer to this H naught as unperturbed or free operator. And the other one is H. So this H is a perturbation of H naught by some other operator V. And so like I can tell you right away that this theory is a perturbative theory. So we can always think that this V in some sense is a small perturbation of the actual operator H naught. So now, after that, what we do, since we have self-adjoint operators, we can apply the spectral theory. So we have a spectral theorem for both H naught and for H. And if so, we can generate these evolution groups. So it's a commutative group, which can be defined just by applying the spectral theorem. So one is e to the ith naught, the other one is e to negative ith. And each of these operators here is unitary operator in the Hilbert space. Again, that's immediate from spectral theorem. And then what we do, we combine them. So certainly in general, H and H naught don't commute. So we take the product of these two commutative groups. And then what we can try to do, we can try to send T either to plus infinity or minus infinity. And ask the question, do we have a limit? Okay, so if this limit exists for every function f in a Hilbert space, and this limit is understood in a strong sense, so in a strong topology, meaning that I'm taking the norm coming from the Hilbert space, and these limits are limits in norm. So if this is true, then we say that the Merler wave operators exist. And they are defined that way. So they are defined for this pair H naught and H. So give me two operators, I can, in principle, as long as these operators are self-adjoint, I can form this limit, and the question is whether this limit exists or not. Okay, so what are they good for? So what can you say if these Merle operators exist? So you can actually say a lot. So first of all, these Merle operators are always isometries. Well, that's just because every single operator here preserves the norm. And secondly, if H has purely AC type, so it should be H naught. If H naught has purely AC type, then this operator right here, the Merle operator, establishes the unitary equivalence of H naught and the restriction of H into the AC, into the range of this wave operator. So that follows from intertwining property of this wave operators. And so in particular, if you know that there is some AC spectrum for the unperturbed operator, then this AC spectrum of unperturbed operator H0 will be inside the AC spectrum of the perturbed operators. In particular, you can establish the existence of the spectral type. Okay, so another notion, if you know that these ranges coincide with AC subspace of operator H, then the operators W plus minus are called complete. Okay, so and another remark is that these wave operators are important, and they were actually introduced to study dynamics. So suppose that you take some function f and apply these wave operators to this function f. Well, you get two functions f plus and f minus. And then if you think about the definition of the wave operators, that essentially means that the action of the perturbed group on this f plus and f minus asymptotically is equivalent to the action of this unperturbed group on the function f that you started with. And this perturbation, of course, is this little o is in a sense of the norm coming from the Hilbert space. So certainly this evolution is a solution to the general non-stationary problem. If you call u of t this e to ithg, then this u will be solving this problem, and the initial date is going to be this g. And so the idea is that usually you take H0, this unperturbed operator, which is fairly well understood, and then you perturb it by something. And then if you have these wave operators, then you can say that for some functions, specifically in the range of these wave operators, the evolution, the perturbed evolution, and this is typically a solution to some partial differential equation, is asymptotically the same as unperturbed evolution. All right, so I hope you I convinced you that these wave operators are important, and they were studied a lot. That's a classical topic in operator theory, in mathematical physics, and partial differential equations. And so in this general scheme, you can put, say, for H0, you can take the Laplacian operator, and then this H becomes a Schrödinger operator. For H0, you can take unperturbed Dirac operator from relativistic quantum mechanics, and then H is going to be perturbed Dirac. And even the wave equations can be studied in that framework, and I can mention many papers, but people like Hermande, Carter, Biermann, Mark Rain, Lux, Moravitz, they all worked on spectral theorem, scattering theory, and they studied wave operators. So what are the basic questions that people want to understand? So it's a question of existence and question of completeness. So let's look at the one-dimensional situation. And in a one-dimensional situation, like Alexei already explained, perhaps the most general framework to study the problems with a simple spectrum is to look at Krein-de-Branche canonical systems. And then immediately, if you want to study wave operators, you need to decide what is going to be your free operator, what operators you want to perturb. And one can say that maybe the canonical choice for that would be this canonical operator, which comes from the spectral measure, which is just the Lebesgue measure on the whole real line. And so if you decide to do that, yes, you can introduce the corresponding framework, and you can introduce wave operators and try to study them. Well, there are some technical difficulties because the whole Hilbert space depends on the choice of canonical system, and it depends on the choice of Hamiltonian. But so there are ways to fix it, and ultimately you can completely understand the problem, and the problem of existence of wave operators has been settled. That's a recent preprint of Roman and myself, and it's coming up. I hope it will be finished fairly soon and available on archive. So this discussion for the general case is a little bit complicated because well, it's technically involved, and just to formulate the result, I will need more than just 1 hour. So let me focus on one particular important case, and specifically on the one-dimensional Dirac operator. So what are one-dimensional Dirac operators? So they are coming from relativistic quantum mechanics. So the one that I have written right here, and so rather I would say that this is a case when the actual relativistic Dirac operator comes with some symmetries like spherical symmetry, and but that's not only it. So in solving some completely integrable systems, to realize this inverse spectral transform in lax formalism, one has to study these Dirac operators, and they are given by the following differential equations. So let's see. So I will be looking at Dirac operators on half line. And so again, there is a signature. This is a constant matrix J. And so then you have this function Z, but Z has 2 components, right? It's a function with 2 components. It's measurable. And so formally speaking, what you do, you take this function Z, and then you take the derivative. So later I'll explain that actually the functions in the domain of definition are all absolutely continuous. So this is completely legal to do that. And then you multiply with this signature matrix, and then you add this potential Q, which itself is the matrix of that form. So you see, it has a special structure, but this is one of the canonical forms for Dirac operator. So you can take any other self-adjoint Q and reduce it to one of the canonical forms. And this is one of the canonical forms, so there is no loss of generality to study exactly those Qs. Okay, so what are those Qs? So Q1 and Q2 are real valued, and locally they are in L1. So you can imagine that in this setup, the unperturbed Dirac operator is going to be the one which comes from making Q identically equal to 0. And now if you want to put it into the framework of what we talked about before when I was introducing the wave operators, then we will need to say that H0, the unperturbed operator, is D0. So it's just going to be this first term right here. And so then potential is this V is just a multiplication operator by this matrix valued function. And what we take for the Hilbert transform, for the Hilbert space. So the Hilbert space is going to be just the standard Cartesian product of L2. It's a space of measurable functions Z with 2 components, so that this norm is finite. Okay, so this is advantage of working with Dirac operator. If you change Q, if you switch on the perturbation, the Hilbert space does not change. So there are some advantages of working with Dirac, but there are also some disadvantages, and I'll explain it later. Okay, so the domain of definition for this operator can be described this way. And so the first line, the second line are quite obvious. So basically, if you want to make sense out of this, you need to have 1 and 2. And the last line right here is just telling you that we prefer to work with boundary condition, which is given by this condition that the second component, Z2, the component Z2, remember Z comes with 2 components, Z1 and Z2. So Z2 is going to be 0 at the origin. So this will fix the boundary condition. And after doing that, this operator becomes a densely defined self-adjoint operator in the Hilbert space. Okay, so having said that, we move on. And so I want to introduce a generalized eigenvector. It's going to be solution to this Cauchy problem. So here, certainly in the right-hand side, you put Z psi, which essentially means that I'm solving the Cauchy problem. And I'm keeping this boundary condition, which I explained in the previous slide. All right, so having said that, we can introduce a generalized Fourier transform. And this is very similar to the discussion of the previous speaker. So now, although I'm doing that in the context of the Dirac operator. So what we have to do, we have to take this Hilbert, so the inner product in the original Hilbert space. And so this map is going to be actually isometric map from L2 D naught. So this is original Hilbert space, and L2 with respect to some measure. So this measure is called the main spectral measure of this Dirac operator. And this is related to the spectral measure that Alexei mentioned. All right, why is that? It's because I'm making this claim that if you look at this Dirac operator, you can put into the framework of canonical systems with a specific class of Hamiltonians. And there is a direct connection between Dirac operators and canonical systems. And this connection goes one way. So if you study very well the problem for canonical systems and get the final answer, so there's a good chance that you can sort of transfer this answer to the framework of Dirac operators, and that's what I'm explaining to you now. All right, so if you want to understand wave operators, you'd better first understand the dynamics of unperturbed operators. So let's look at the free Dirac and try to understand everything about the free Dirac. Well, this is a calculation which is very much explicit. So the generalized eigenfunction can be computed. It's a cosine and sine. So the Lebesgue measure is going to be the main spectral measure of our operator. And so to understand the evolution, well, you can do one thing. You can just compute it and get the answer. And this answer is not going to be that pretty, but in this formula, you will sort of see that some pieces of the functions are being translated. But I'd rather do the following. So I'm going to show you that by a very simple algebraic tricks, you can put this Dirac operator and its evolution, and you'll just see that this is just a standard shift operator. So let's do two very simple unitary transformations. So the first transformation is taking this Dirac operator D naught and sandwich by this constant metric Z. So Z is unitary. So that's just a change of variables, if you like. So we perform a change of variables on Hilbert space, and this is a very simple one. All right, so if you do that, you come to this form for this new operator D naught hat. And but remember that there are also boundary conditions, and the boundary condition will change to something. So you can see like how every boundary condition that you started with is going to be changed under this change of variables, but you don't stop there. So then the Hilbert space after this conjugation is going to be the same. It's going to be the same Cartesian product of L2. So it will have two components. It will have one component F1 right here and another component F2. But we have two functions in L2, each one is sitting in L2 of R plus. So what I suggest to do is the following. So I now form the function G, which is a function defined on the whole real line. And for positive X, you are picking up the first component. For the negative X, you are picking up the second component of F2 and multiply by I. So then if you do this transformation, then you can show that the original operator D naught, the unperturbed Dirac, is unitarily equivalent to this operator on the whole real line. And if you look at this operator negative I partial derivative in X on the whole real line, you don't need boundary conditions, you don't need anything. It's going to be self-adjoint operator with domain of definition, which is a Sobolev space of degree 1, right? And the evolution, the evolution group for this operator, it's just a standard familiar shift. So then if you see how this shift works, you can start with the function, do the shift, and then undo all these unitary transformations. And this is going to tell you what is really the dynamics of the free Dirac. So that is just a shift. That's my clue. Okay, but we are interested in doing the scattering theory. We're interested in studying the wave operators. And this problem in the context of Dirac, and especially the Schrödinger operator in dimension 1, has been studied really extensively. So what would be the natural framework? So you would take potential Q in some scale. So the natural scale is the scale of Lebesgue spaces, LP. And you would ask what is the optimal P for which the wave operators exist in the Dirac framework, or maybe Schrödinger framework. So if P is equal to 1, you can apply immediately the theorems of Crane and Biermann to say that actually there will be wave operators. You can just apply the trace perturbation argument to do that. But this is a special case. You would want to study some specifics, and so there were many papers. There was a lot of work about 20 years ago, especially in the context of the Schrödinger operator. And so what people noticed is that if you take P larger than 2, then you might produce purely singular spectrum. The AC spectrum can be destroyed completely, so there is no hope to get wave operators in this situation, because wave operators necessarily imply that there is some AC spectrum. All right, so then what is the borderline case for the existence of wave operators? So if P is smaller than 2, then there were papers by Chris Kisielov, Simon, Last, and Tremblin, and that was maybe 20 years ago. And so these papers were very important. So they were trying to establish the asymptotics of generalized solutions, the generalized eigenfunctions for almost every energy. But in fact, the sharp result can be obtained through the shortcut. So you don't have to actually prove a strong result about almost everywhere convergence, and you don't need to estimate the maximal functions. So in 2004, I proved that P, which is equal to 2, is actually the optimal choice for the existence of wave operators. So in that case, these operators, they exist and they are complete. And the proof was not difficult at all. It was maybe 4 or 5 pages. Important thing is that it's been used in a complex analysis, and it's been using some ideas coming from polynomials orthogonal on the unit circle. Okay, so now in that scale, the problem has been resolved, but you can ask, so what is really the criterion for the existence of wave operators? So we have the sharp result in LP scale, but what is really the criterion? Well, maybe it's too ambitious to ask, but in fact, the answer was found. And this is something that I want to explain. So to do that, I have to give you a few definitions first. So suppose we are looking at some measure on a real line, and all I need from this measure is that it's Poisson finite. So Poisson finite, so Alexei already said what it means, but you take that measure and integrate with the Poisson kernel over the whole real line. So the result must be finite. That's Poisson finite measure. Okay, and so then I say that this measure is in the Sergey class if its logarithmic integral is finite. So you take log of the density of that measure. So here I assume that this density is non-trivial, right? Almost everywhere it's positive, otherwise the logarithm will blow up to negative infinity. So you take this logarithm of the density and again integrate with Poisson kernel, and you should get some number which is not equal to minus infinity. And if you, so just a remark that if you apply Jensen, you see that this integral is always smaller than plus infinity. If it blows up, it can only blow up to negative infinity. Okay, so we give this name the Sergey class, but in fact, it just existence logarithmic integral. And so what I want to do, I want to formulate the recent result with Roman. and it's in production. So here the mu sub d is a spectral measure for Dirac operator. So this is important remark. That's not just any Poisson finite measure. It's the one that comes from Dirac. And if it comes from Dirac, it also has some extra assumptions because in Dirac, my coefficients are in L1 locally. I will not get into that, but rather than that, there are no any restrictions. And I want to look at the diagonal potential Q. So we studied Dirac with diagonal Q, and then the three statements are equivalent. So the first statement is that this measure is a Sergey measure. So this is how you can tell, looking on the Fourier or looking at the spectral data, what you have, right? So this is equivalent to existence of wave operators, the standard Merle operators that we talked about. And this is really equivalence. It's if and only if. So if you have the spectral data, looking at the spectral data, you can tell what happens with wave operators. But what if you don't have spectral data? So what if you have just a potential? You are given potential, as it's typically done in mathematical physics. You are given a particular Q, and you need to decide whether you have wave operators or not. Okay, so the answer is formulated in that way. So what you have to do, you have to first form, well, first there is this integer lattice by n's. So you take every n, you integrate the potential from n to tau, then take exponential of that. It's no negative function. And then you form this, this product right here. So this product sort of, it resembles a little bit the Markin-Haupt A2 condition, but you integrate. So, and especially if you divide by this 4, it will be exactly the averages in the Markin-Haupt condition. But now you fix the scale. The scale, the intervals of which you are doing the averages are all of fixed size. In that case, it's 2. And then once you check that this sum is finite, well, that's a criterion for the existence of wave operators. And that's a criterion for the measure to be in the Sergey class. So that's a connection between spectral data, potential, and the dynamics. And on top of that, we can show that if these wave operators, if they exist, then they necessarily must be complete. Okay, so as you see right here, I've been using a particular form of the Dirac operator. It happens to be diagonal. So this is a case in which the answer can be done in the most simple way. But don't get me wrong. So in fact, the statement is the general statement for all potentials. You can add off-diagonal terms, but the solution is not going to be that pretty. So this connection with the Sergey condition stays the same, but this characterization in terms of actual entries, it's also explicit, but it's not very pretty to write down. Okay, so this problem of existence of wave operators for Dirac has been settled. And so let me just tell you that if you want to shoot for the most general Dirac operator, then even the definition of the wave operator needs to be fixed in the sense that you must allow this freedom of multiplying this combination with some measurable phase. So here this gamma is actually E I phi, and phi is some measurable function on the real line. And this phi accounts for some rotation, which sometimes happens. So you cannot drop this gamma. Sometimes it's just absolutely necessary. Okay, so what I formulated is just an application of this general theory of scattering theory and wave operators for canonical systems. You can apply the theory not only to Dirac, but to the vibration of the Crane string. And I don't have much time to explain the methods of the proofs, but sort of the roots actually come to the theory of polynomials orthogonal on unit circle. So I would say that we've got most of inspiration there. It's a classical complex analysis, And so what you have to do, in fact, you have to study the asymptotics of the generalized eigenfunctions psi when z is fixed in the upper half plane and this parameter tau goes to infinity. So you do that first and you relate this asymptotics to the properties of mu, and then you do your analysis, and after some work you get all these characterizations. So that is not 5 pages as in my first paper. It's much longer because one has to establish the connection to the actual potential, and this condition right here doesn't come for free. So nothing comes for free, but this characterization is completely settled in the context of Dirac operators and actually in the context of canonical systems too. So like I said, this is our recent preprint with Roman, and now I want to use the rest of my time, about 20 minutes, to talk about the multidimensional situation. So in multidimensional situation, you certainly understand that there is no such a neat theory like the theory of Krein and de Branch. So one has to sort of invent something which is borrowing a bit from that one-dimensional theory, but necessarily one has to use the technique of PDE. So I want to illustrate that development looking at one particular problem. So this one particular problem has to do with this operator, which is a classical operator in partial differential equations. It's elliptic operator, and it's elliptic operator which is written in the divergence form. So what you do here, you take, it's going to be only 3-dimensional case. And so you are looking at this form. So that's a gradient, that's a divergence. And in between, you have some potential. So this potential V comes right here. So suppose that V is equal to 0, then you must get an unperturbed operator. Well, what it is, it's a divergence of the gradient. So this is the standard Laplacian. And since I want to work with operators which are non-negative, that's just the tradition in that business. So I'm putting negative sign right here. So for the Laplacian defined on a whole space, we know everything. The spectrum is purely AC and it's sitting on a non-negative real line. It's purely AC, it has infinite multiplicity. And this infinite multiplicity is actually the key problem. It's a key difficulty for spectral analysis. And so then the dynamical problem that I want to study is the following. So instead of working with Schrödinger evolution, I want to look at the acoustic equation. And the acoustic equation comes with this setup. So you have second derivative in time, and it's equal to negative h. But since we have second derivative in time, once we assign the Cauchy data, the initial data, we need to have 2, right? Because so the first data we have is the value when time is equal to 0, and the second initial value that we have is initial derivative in time. So this problem can be very easily explained. So if you talk about sound waves, so this is your initial displacement, or maybe initial pressure. And that will be initial derivative of the pressure. So you need to assign both to actually have the well-posed problem. If you talk about the vibration, if you talk about vibration of an infinite matter, right, then it will be initial displacement and that will be initial velocity. So it all makes sense and has been studied extensively. So so again, if you assume some information about V, and I'll tell you exactly what we need to assume, then this operator H becomes self-adjoint in the Hilbert space L2. So the Hilbert space again is L2 on the whole R3. All right. Then yet again, so we want to understand the unperturbed case. So if V is equal to 0, what is going to be a solution to this acoustic problem? And it's again well known is given by Kirchhoff formula, which I have written right here. So whenever I take this parentheses like with angle, that's just a standard averaging. So here I'm going to be averaging over that sphere of radius t centered at x. That's a sphere. And if you look at that formula, you realize that, so what happens is that if you have initially U0 and U1 compactly supported, then the wave will start going ballistically in all directions. And the feature of the three-dimensional case is that, so it will leave your origin and it will never come back. So you really have a front, and this front propagates ballistically in all directions. So since we have a formula, we can tell everything about the solution. And now we have this perturbation given by V. So the question is, under what minimal assumptions on V, the wave still propagates? So this is exactly captured by wave operators, but now this wave operators are supposed to be acoustic. So how do you do that? So instead of taking the operator itself, all you have to do, you have to take the square root of this operator. Well, clearly for that, you need to make sure that these operators are non-negative. Otherwise, the square root will, it's actually, it is going to be defined, but it will give you some imaginary parts which will contribute to non-physical behavior. So you'd rather assume right in the beginning that every single operator from which you take the square root is non-negative, then everything is fine. You can still use spectral theorem to define these objects. And so if these operators exist, then these are called acoustic wave operators. And if they exist, you can again say a lot. You can say that AC spectrum is present. You can show that some waves, they travel ballistically, and you can say something about the asymptotics of solution to the acoustic problem for a long time. And again, so the question is, under what minimal assumptions on potential you can say that these wave operators exist. And again, so that problem has been studied extensively, and for potentials which are, say, compactly supported or decay very fast at infinity, that problem has been settled and in the framework of the known methods. So what I want to do, I want to present new point of view, which is using complex analyses. And we are talking about new methods, rather some particular results. But to explain these new methods, I have to formulate some particular results. So that's one of them. So I have two conditions. I have two conditions on V. So the second condition, maybe I'll start with condition B first. So it's a very simple one. It's just saying that 1 plus B stays away from 0. And I need this condition to make sure that this operator H is non-negative. It's just to be able to take the square root. So this is pretty much a necessity. Without this condition, nothing can work. So there is no well-defined dynamics. Okay, the first condition, condition A, is more interesting. So what we have here, we have this amalgamated space. So let's look at this formula first. And what it tells you is the following. So you have a function, then you restrict it to this annulus of size 1, right? So the radii n and n plus 1. And you read off the L infinity norm of your function there, and then you just do the standard little L2. So it's a combination of L infinity and L2. It's a mixed norm, which is sometimes called amalgamated norm, because you do amalgamation in the radius direction. Okay, so, and then the theorem, which I proved some time ago, it says that if you take potential V, which satisfies both conditions A and B, then these acoustic wave operators will exist. And so, again, so they exist in a sense that you can take every function f in L2, and this limit will be the limit in L2, the limit in the standard Hilbert space. And recall that H is this divergence-free operator defined like this. So in a sense, this result is sharp. If you drop this condition L2, or rather if you replace it by condition LP with P larger than 2, then again, there are examples when the AC spectrum disappears, and so there is no WO. And if you think about what you have here, so this V is represented as a divergence of the Q, and Q decays fairly slowly, right? So as a matter of fact, this is telling you that your potential, your medium at infinity, sort of it converges to some constant one, of course, but you have local oscillations coming from this divergence operator. But these local oscillations are very, very small. So you can allow very small oscillations. Well, you might wonder, so do we have some realistic examples of potentials like that? And in fact, there are quite a few. So these are examples with slow and random decay. So what you have to do, you just have to take some profile like this. So there is no randomization yet. So instead, what you do, you take xj's points in R3. Well, you can think about just taking the integer lattice points, and around every single lattice point, you put a small bump phi. Phi is right here. And then every bump phi comes with the amplitude aj, and this is your model. So then what you want to do, you want to make sure that these aj's are chosen so that we have this relatively small decay. So this decay is the weakest assumption among all assumptions in the literature. And this decay is sharp. So here epsilon is arbitrarily close to 0, but this is not yet the potential for which we can formulate the result, because there is no any randomness yet. There is no any oscillation. So to get the right oscillation, all you have to do, you just have to randomize. So every amplitude will come with randomization. So these CJs are IIDs. With some very mild assumptions, but if you assume that these CJs are Bernoulli, that will be good enough. So this is exactly the model that has been studied by Borgen and Rodnyansky-Schlack. And so here I'm actually proving some deterministic result, and then I show that almost surely this model satisfies the condition of this deterministic result. So that's the idea. So my basic point is, I guess, that there are many, many potentials for which these conditions of the theorem are satisfied. Okay, so then now I think that I don't have much time, but I still want to explain a few things about how the complex analyses can be used to solve this problem, to get these results. So there are no entire functions in this business, and we have to substitute it by something. So what do we do? Okay, so we start by saying that, well, let's take this operator H, it's self-adjoint, and I'm going to look at the resolvent. So this is H minus Z inverted, and this makes sense for every Z away from the real line, because operator H is self-adjoint, just a spectral theorem. And then you say that since we are dealing with the particular operator, which is elliptic, we can say that this resolvent is represented by the Green's kernel. And so now we have a concrete object that's a Green's kernel. And this is a function of 3 variables. So Z is a spectral parameter, and X and Y are points in R3. So what the central object of that theory is going to be to look at this amplitude, and the amplitude is a ratio of perturbed Green's function and unperturbed Green's function. So fortunately, the unperturbed Green's function has no zeros, and this division makes sense. And both functions here are going to be functions in K, and K is the square root of Z. And since the resolvent is analytic in Z, one can show that every single function here is also going to be analytic in K. And that will be the key connection to complex analysis. So analyticity of these functions in K is a key feature which allows actually to prove the results. Okay, so then what do we want to study? So if you say that we take potential which is relatively small at infinity, decays, then we can assume that the Green's function of the perturbed operator asymptotically is going to be close to the perturbed one. So then we take X to infinity in some direction by fixing Y. And then what we have a function which is defined. So it depends on Y, because we fix the base point right here. And then it depends on K, because that's your spectral parameter. And it also depends on the direction along which you are trying to go to infinity. So we have this structure. And so already Eggman looked at this problem, but only for short range case. And he proved some convergences in L2 topology. So this S2 is referring to the angle in which you want to go. And so the key theorem which allows to prove the existence of wave operators is the following, that under conditions A and B, and fixing every point Y, one can say that there is some limited function right here. And so what we do here, as you see, we fix this A and we restrict to the sphere of radius R. And then we take the limit. So what topology I'm using right here, it's this L2 S2 topology. It's not the pointwise topology, rather it's topology inherited from L2 on the unit sphere. And then this function A infinity that you get is going to be a function which depends on Y, but this dependence is not so important. It's going to be a function which depends on the angle. And this dependence is absolutely crucial because that's exactly the topology I'm using right here. And also it will depend on K in an analytic fashion. So now this function that I see right here is going to be vector valued analytic function defined in the upper half plane. And this is a key object that one wants to study. And so here one has to prove a few things about this object. Now, what's the key thing that allows you to actually study this function? So the key thing is the following factorization identity. So if you look at the actual spectral measure, you can call it mu. And so the density of that spectral measure is going to be bounding the L2 norm of this function A infinity. And this is an a priori bound, which essentially allows you to say that this function A infinity, it's kind of the function in the local Hardy space. And this Hardy space is not a scalar Hardy space, rather it's a vector valued Hardy space. And so the target Hilbert space or like these components that I'm choosing, these are essentially elements of S2. So combining these two things, one can prove a lot of results. In particular, one can show that if you look at the spectral measure of some function f with compact support, then the spectral measure will satisfy the finite entropy condition. So this means that if you take that measure and look at the density of this measure, then the logarithmic integral of this density will be finite over any interval I, which stays away from the origin. So if you like, this is the analog of the Sergey condition that we talked about in the one-dimensional setup. Okay, and so then having established that, so this is enough of results to actually prove something about the dynamics. So then you can make the connection between dynamics and the resolvent by writing down this contour integration. And I'm not sure I have time to actually get into all the details, but so then this very general result, which one can show for all operators, has to be adjusted to the current setting. That's the particular lemma that one has to do. And so maybe I'll skip that, but ultimately the corollary is that you can write down the wave operators through these amplitudes that I defined right here. And so this whole situation becomes very concrete. And this is the last slide. And I think I'm done with my talk. Thank you. Thanks a lot.
Thank you very much. We have time for questions, comments. There is a question in chat.
Yeah, so one question is, this applies also to transversal sound waves discovered recently. I don't know. I never thought of this. So most likely it's not exactly the case, because my waves are, well, not my waves, but these waves that I study. So these are really just a perturbation of the spherical outgoing waves. If you want to study the wave which goes in a particular direction, then maybe one can say something, but I don't know. So one has to first do some analysis on a PDE level, and then maybe from that you can make some implications about existence of dynamics, but I cannot tell.
Good. Other questions? If not, then let's thank our speaker once again. Thank you very much.